to make a disclaimer. So I'm here not representing Intel, so I'm not going to talk about internal things or even the project that I will mention, however, that Intel Media is a new venture that is working on internet TV. Maybe you have heard a little bit about it, and we are exploring in the space of what we call over-the-top, internet TV, and there's a lot of interest in that space. So, but I will talk about my experience building advertising and recommender systems, and how I found over the years how similar these two things were, and how they can apply. The learnings on one side can be applied to the other side. So in terms of objective, I really want to nail it down to two main objectives. One is that you guys pretty much see the parallels and the similarity between advertising systems and recommender systems. I'll make sure that that happens. The other thing is that talk a little bit about the technology and techniques that are used in advertising systems, which we know how to scale, and see how that can be applied to recommender systems. So, I will then, based on, I do have some introductory slides for the folks that have, basically very little idea about these two systems. I'll try to go through those quickly so that we can go to the meat of the presentation. So the agenda is pretty much an introduction about recommender systems, introduction about advertising systems, an example of how an advertising system works, in this case a video exchange, just to illustrate. We'll go and see why and how these systems scale. We all know that advertising systems are pretty much prevalent in the web, and not only for banner, display, or search. We're talking about video, obviously TV. So it ranges across devices, across different areas. And then we'll talk about how do we, when we go to how we scale these systems, we'll give specific examples of how to build advertising systems, and you will see then the parallels and how to apply them to recommender systems. That's the idea. At the end, I also want to brief mention the whole problem or the crux of measuring or being able to evaluate these systems, which has been somewhat a problem in the past, specifically on the recommender system side. So, eBay, it's up there. So basically, recommender systems, people, when they hear about it, they tend to think about, okay, what Amazon recommends in terms of products, what eBay has on their website, video, very much the history of recommender systems. This is just a definition that this I borrowed from Wikipedia, but basically the history of recommender systems has been trying to figure out the preferences of the user and kind of figure out and predict the rating that a user would give to a specific item, whether that item would be something that is being bought in a website, or it could even be about people, in terms of matching people to people as well. And it's circa 1980, so it started back then. Primarily, there was research done in the University of Minnesota that was in the what we call maybe familiar with Movie Lens. It's the first data set that was used for data mining and recommender systems, and it primarily had a set of ratings that that users had given to movies, and the idea was, can we come and actually predict what would be the tastes, the interests of the user in a movie that they haven't seen. It has gone all the way to even having prize money, right? The Netflix $1 million prize or challenge would say, okay, can we improve our recommender system? We'll pay and do a competition out there to find out if there's algorithms that we can use to provide us with better recommendations. So, in a nutshell, it has been simplified, and I will reinstate this again and again. The way that recommender systems initially has been modeled or explained is that we have essentially a set of or inventory of items, whether these items are movies, books, or any product. We have a set of users on the other side, and the goal actually is to basically predict how would the user score or rate an unseen entry in this huge matrix. So you think about it as a huge matrix. You have the items and the users, and items of course can be described in terms of features. So we have different features describing the items, keywords, content, etc. We have the set of users, which also can be described in terms of features. And then we could use these features eventually to compute entries in this matrix. What are the approaches? So there's fundamentally two schools of thought, or two kinds of approaches. One has been the collaborative filtering. A lot of people have heard about this, collaborative filtering. Friends of friends or like-minded people think together, similar. Can we infer algorithm that can compute similarity between users based on that matrix, right? And find out if similar users think alike, then probably a person that has been or has seen a movie that is similar to another person may have similar taste or distaste, and therefore extract that rating and try to compute a rating for unobserved items in the matrix. There's also in this matrix, you can think about it two ways. You can find similarity between users. So the user similarity that is used for recommendations. You can also find similarity between items. And again, a lot of this information comes from past history. So you know whether users have seen, touched, bought items. Basically you can correlate or find correlations between any of these two rows, or columns, and use those correlations to basically compute a score. One of the issues with collaborative filtering, well, there's several, but one of the big issues is that what happens if it's a new user or a new item? You don't have history. You don't have an entry actually in that matrix. Well, of course, you could use the features to try to infer some of the ratings, but there's the problem of cold start, which basically you don't have enough information. The other problem is dimensionality. If you're talking about this matrix and you want to fit in memory, well, imagine if you have millions of items and millions of users. How do you do to represent this in memory and kind of make your computation? So there's been work there on what we call dimensionality reduction to try to make sure that we kind of project high dimension matrix into a smaller space or a reduced dimension space, and then do computations on that. There's the second approach, which says, wait a minute, I have features. Features means I have signals. Signals, I can data mine. I can mine those signals. I know what supervised learning is. I can apply supervised learning algorithms, or even, to some extent, unsupervised learning algorithms to cluster, label, and then with the labels, being able to predict what would be the score, the rating, more like a regression or a classification task of this person. Will this person like an item that he hasn't seen in the past? So there are other critical limitations. If you observe the matrix that I talked about before, they mentioned the item and very well described the features about them. They also mentioned the user, right? But happens to be a lot of other variables that are not, and that's the departure part of the traditional recommender system, that have not been really considered in the equation. Most of it is based on context. What time of the day is it? If you're recommending movies, you better understand the time of the day is critical to basically assert how much, which movie is in the mood that the user is in, right? So other things like simple geolocation. There's certain, if you're a person that is also likes to see movies on your mobile device, sometimes understanding what kind of clustering or a group of people are doing based on location may be of interest to you for you to compute similarity and recommendations. And even more granular things. So, for example, the device. Am I recommending a ebook that's dense? I can see it on a big screen, or maybe it's too dense to even look it up in an iPad. So there's different aspects that are subtle but very important when it comes down to recommending items. There's another, I briefly talked about it, it's the problem of scale. So scaling recommender system is hard. So there have been, even scaling machine learning algorithm is hard. So there have been attempts, of course. There's in Mahout, for example, right now there's interesting attempt to make MapReduce algorithms that can compute matrix factorization, or SVD, which is mainly one of the techniques used for dimension reductions. There's also attempts to apply some of these machine learning algorithms, implement them in MapReduce so that you create models that can be applied and then to use the filtering. But then again, we're talking about huge amount of users, huge amount of items. So they're in the right direction, but really true internet scale is hard to achieve. So let's try to restate what, at least what my view of a true recommender system would be, right? So one of them is, yes, we want to delight the user. We want to recommend something that is both contextually, relevant and as well as timely. Obviously, it has to, in some case, not be the same of the same types of recommendation. It has to be more also exploratory. So a lot of recommender systems have another problem. Problem number 2, I mentioned cold start. The other one is portfolio effect, which is once you kind of put someone into a box, like typically, an Amazon case, once you bought some item, then it will again hammer you and bring you recommendations of more of the same, something that is actually not well received. The other thing is, and here's where it comes, the first big similarity and kind of introduction of where advertising systems fit into place. The other thing is that there's no such thing as recommendations in a vacuum. Companies that actually have recommender systems have them for a purpose. Whether it's cross-sell, upsell, there's some actual objective functions being defined in terms of monetization. Guess what? You think that recommender systems are out there just for the purpose of delighting the user? No. Same as advertising system, there is intention behind it, but it actually has to matter to the user. So it cannot be forced upon the user. It has to actually have to matter. And all this, we have to do it at scale. So this is a segue to internet advertising. Now, I will skip some of these slides because it goes into the motivation. But I want to present some of the important aspects of it. Again, a definition here from Wikipedia. I don't like much about the manipulate part, but nevertheless, it is encouraging people, viewers, to showing a message and kind of have an internal drive or commercial offering behind it. So to some extent, it's very similar to recommender system. I think one of the things I really want to emphasize is that advertising has been around for a while, a lot older than recommender systems. It also has a lot of money behind it. So if you think about the rise of online advertising and why does it power, power horses, really big companies like Yahoo and Google, it's because even with the small amount, considering all marketing budget that is really spent today online, the amount of money that it's handling and it's processing, is an incentive to do not only research but live systems that scale and systems that can handle a lot of users, right? And just look at the numbers here. I'm going to skip these, but basically the spending in advertising is huge. One of the things that people really like about online advertising in specific is the fact that you can measure things. And when we were talking, I think the gentleman that talked about sensors for the car, API. When we talk about advertising, we're also talking about a huge amount of sensory information that we capture when users perform an action. Whether that action is viewing an ad, clicking an ad, purchasing something due to an ad being seen, or even just the fact that the user has seen certain types of ads, and all that information is kept and used. So by using the feedback, it's important that even a whole area says, wait a minute, advertising goes beyond search. It really involves machine learning, data mining, and economics. Remember the part that we have to do about money, right? So it's there. So I'm going to just couple of slides here talking about the enabling technology. I think most of these are well known. I mean, the reason why systems in advertising scale is because they're built on distributed computing, right? So we have distributed data processing, you know, the Hadoop, the real-time processing, Storm, and the you know, right now the Amp Lab in California is also doing, in the University of California has this Spark. So a lot of this technology in place to handle and process offline data. Data in the back end. We also have serving systems that scale, and also some advances in marketplace design, which I will talk a little bit about. Okay, so again, this is one thing that I wanted to present, but I think we can brush this a little bit. I think the important thing here about advertising is, one, there's the concept of audiences. So audiences are, who do we want to target? How do we want to present an ad to a specific group of people? There's the concept of, as we were saying, the analogy here is when you talk about audience, there's the users. When we talk about publishers, which are mentioned here, it's the place where you're actually going to show and send the ads to, or a recommendation. There's advertisers, which are the producers of the content, in this case, that you would like to show and recommend to the user. And there's the actual creatives or ads themselves, which is actually the items or the representation of the items. So how are audiences selected? Turns out that targeting, many people have heard about the word targeting, is one of the key problems of advertising. How do you handle constraint? And it becomes a constraint satisfaction problem where you say, I want to target, I want this set of ads to be shown to a subset of the user in a subset of the space of the user within this particular location, and also in the page where I'm going to show the advertising, there needs to be these words. So those are constraints that are pretty hard to satisfy, and actually at scale it becomes harder. And you also gain information about what I classify the user into segments. So basically I can say behavioral-wise, based on what they've seen in the past, what they've clicked on, you know, I can classify them as, for example, sports enthusiasts, or you know, so it's not only dimension in terms of demographics, but also in terms of behavior. So I'm going to skip this. A little bit about the pricing and advertising. And I hope most of you heard of the word CPM, but basically that's how advertising is kind of the currency in advertising. And then there's also CPC, CPA with respect to how people pay for advertising. So you can show something to a user, but some advertisers only pay on click or only pay when the purchase happened. And the reason I'm showing this is because there are actually parallels with the recommender system, so that I want to talk about later. One
question.
important aspect, go ahead.
With internet advertising systems, sometimes there's a problem of who gets credit, because a person might go on multiple ad networks to promote, and that might just choose, well, the last one to display a banner gets the credit, but maybe if the previous one displayed 100 ads correctly to the right person, should that get some credit? Just bringing that up as you're making your analogy, if that's something.
Yeah, attribution is very important, and attribution over time is important. And most of the, especially on conversions, attribution happens within a period of time. So we're not talking about what, you know, an ad could have been seen, but actually attributed to the advertiser. And typically it's the latest one, and also sometimes there's an average, a weighted average on how you attribute to a specific advertiser. But it's very important to understand that you know, who gets the credit for it. Now, one important thing is the mechanism how advertising systems make decisions. I did briefly talk about you know, different kinds of advertising systems. I'm not going to go into the details of what's called guaranteed delivery or non-guaranteed delivery. I will make the slides available. But one thing for the spot market, what we call non-guaranteed delivery advertising systems, there's actually a very sophisticated you know, mechanism of an auction determining the winner. Sometimes these auctions happen in split seconds, and obviously there's bidding going on where the bidders are the ones representing the advertisers, in terms of I want to get this opportunity and show my ad for this opportunity. Obviously then, but it's not just economics, because if you bid high, but it turns out that the ad you show is ineffective, then how do you penalize that in such a way that you are relevant to the user? Remember, we are all about making sure that the user is matched with an ad that is actually meaningful for them, right? So these mechanisms include bids, but the bids are not static bids. These bids are fluctuating according to some models. And they represent not only a value that is assessed by the advertisers, but assessed by the system to know how effective they are over time. So just a summary about advertising. So in general, there's channels. So you have a lot of different channels. You have the search, the displays channel. There's social advertising in Facebook, which is kind of a segue to, it's a display with a twist. You have email. You also have video advertising, which is more like the formats, right? So you have text, you have images, but you also have video and different kinds of devices. And again, different kinds of pricing models, whether it's pricing per thousand, which is the CPM. I pay for thousands of ads that are shown, which irrespective of what the user does, or I only pay for an action that the user does, or whether it's a click or an auction. An action like conversion is different kinds of advertising schemes here. So let's give an example. And here's just a very simple example. By the way, the core of advertising works very similar. This in particular is an example of a video exchange. But the same thing applies to display in general. So what happens here is that a user's looking at something. They're looking at a website. And turns out to be there's a video there. So video ad, the way it works is that you want to show a video advertisement in front, let's say a pre-roll ad in front of the actual content itself, or a mid-roll in the middle or at the end when the user sees a particular movie or a particular show. So one thing that's very interesting here is that when an advertising request comes into these systems, let's say an exchange, the exchange actually has relationships with data companies that have collected information about users. And this information is across websites, across different systems. An example of these systems are BlueKai, Target Info. I believe that there's different there. What these calls are, basically these are data platforms, data management systems that have collected information about users and made them available through segmentation, through segments that are used for targeting. Remember I mentioned behavioral? So these actually recognize that you have been seeing some sites that are related to automotive, and therefore you may be an automotive enthusiast. And that is provided real time for targeting and decisioning on the ad side. Then the advertisers come in and they're just there with some bids, right? But turns out that this information is used to find the match. And then the ad or the pre-roll is shown in front of, for the user. How does this really happen? So essentially you have an exchange, a publisher, yeah, I need an ad, great. So in the case of video, there's something called VAST. There's a protocol where basically I request a call, and it's actually, the exchange returns back an XML document, which contains pointers to the actual ads themselves. Sometimes they contain redirects, but essentially it contains information for the player to obtain the actual pre-roll ad and show it to the user. So internally what happens is that there is an ad server involved. So when the user starts and clicks the actual video, based on the XML document that it was returned back, then essentially a request for the actual ad happens, a decisioning in milliseconds happens, and then it's shown back to the user. And there's a lot of redirects happening in advertising because you have the place where you actually store the video, the first-party decisioning system, which may not have the right ad. So it may forward chain to another system that actually then has an ad that it's right match. So you see a lot of what's called redirects in order to find the really good ad. And by good, we're talking about who pays the most. So there's an optimization of revenue for the publisher, but it's also optimization for the advertiser, because there has to be return on investment. So, given that, how do we scale? And this is really the meat of the whole presentation. Well, a lot of these ad systems were born looking at how people do search. So that's why, guess what? Google and Yahoo's are the world are very much powerhouses there. Turns out that if you can, if you have items, in this case ads, and you want to serve millions of users, you have to be able to partition and spread across, do scatter-gather across a bunch of servers that contains partial information or information about the ads, and they basically partition based on hashes of hash number or hash of the ID of the ad, so that you basically load balance across a bunch of servers that will be able to serve to you. So there's the concept of an index. Sounds familiar with search, right? There's also the concept of a model, because ads are based on bids, right? I mean, the mechanism, the decision making is based on bid. So you have to have a way to compute the bid. So there's this concept of that you have internal representation of an index to be able to quickly search and retrieve and basically apply constraints to get the ads. And you also have to have models to be able to compute the bids. And the bids, guess what, are not only related to the value that the advertiser has given. Remember about relevance, and also remember about budget. Advertisers have certain budgets, and these budgets run away, so you need to understand how these budgets are well distributed across. So it's a fairly complicated optimization problem. And people say, well, partition, everyone knows that. Obviously, then everyone knows that not only partition, you have to have replicas, because that way you scale across machines, but you also, if one machine goes down, you have a way to recover and reply with responses. So essentially you have some kind of meta server, meta auction, where the results come back, and then you can basically fan out to a bunch of machines which have local auctions, produce bids, and then you can come back with results and match right with the ad. So I think the million-dollar question is, how do we produce the bids, right? Because if you produce the bids right, then you can actually solve the problem of advertising. Well, here's where data mining comes into play. So remember that I talked about models, right? So most of these systems, even when we talk about indexing websites, they're all about how you crunch numbers and get the information of where these words occur to create a inverted index. We'll talk a little bit about that. That can be partitioned and shown around. There's also a need to create models. So you have a feedback loop, however, in the process, because you have the, let's call it OLTP. I don't like the names, but that's basically what people sometimes refer to. An online transaction, essentially the place where you gather information about a transaction. A transaction could be not only a purchase, someone purchasing. It could be an event such as someone scrolling, in a website, or fast forwarding in a video player. So all these events are captured and transmitted to a transaction data inventory that then is analyzed, guess what, to do two things. One, of course, is to take that information and feed it back into a model that you can then put it into these servers. Remember that these servers contain a model, so you need a way to compute offline, and because you don't want to have a live transaction system that queries a database, those models need to fit into memory. And the way you do it is basically by partitioning with models associated to individual items, and then computing on the fly. Each node should have a way to make the decision and create bids. The bids are not pre-computed, though. They're just the models that are pre-computed, so when the request comes in, then the bid is computed. All this also has to do with traditional reporting, because then you need to know how these things are done. So now let's look at a little bit more in detail of what happens with an ad request and what are the steps. And again, I'm going to make reference to recommender systems at this point. So first step, eligibility. We have constraints. These constraints are defined by the publisher. Let's say I'm a movie recommender systems. No reference to Intel, please. But basically, I have a movie recommender systems, and I don't want to show certain types of, recommendations of movies for this particular section of my app. That's a constraint that is defined by the publisher or the place where essentially the ad is going to be shown. There's constraints by the advertiser. In this case, the advertisers think about it as the person that's providing the content. This content cannot be shown to people it's rated R, so it has to be 18 and above. So there's constraints there, regardless of whether we think about it in terms of recommender systems. There's clear constraints that are happening that are defined by the publisher, defined by the advertisers. In other words, targeting becomes an essential way of defining how recommendations are actually going to happen. And I'm going to go back and forth between recommender systems and advertising systems here. Second one is ranking. So when I have a way to select what is eligible, I need to be able to rank. In the advertising world, it's to create a bid. If I rank it with creation of a bid, then the auction takes care of selecting the highest score. So in terms of ranking, it's very important. And then there's delivery. So there's, I need to be able to pace my delivery. Some cases, in the case of advertisers, they don't want to spend all the budget at once, right? So even think about it in terms of recommendations. Do you want your, all your recommendations for a particular item to happen in the same day? Sometimes there is a need for kind of spreading out and letting people get recommended certain items based on some constraints on delivery. So now let's come back to the problem of constraints and how we define constraints and why this is scalable. So let's talk about just a Boolean expression of this kind, right? So it's basically an age within a range group 10 to 20 and country not US. That's basically a constraint that can be defined either by the publisher or the advertisers. We don't care at this point. There's also an assignment. Okay, so there's an assignment when the user comes to the website or is going to see a movie. They are recognized to be within a certain age range, coming from a certain country, probably all the other things that we talk about behavioral targeting, right? Where you can actually query other systems to know how much you know about them and then use that for targeting. And then the problem becomes, one of the problems is, given an assignment S, how can we find all the Boolean expressions that matches this assignment, sorry. So here's where the whole thing gets kind of summarized. Remember about search, and I said that search was the cornerstone to create advertising systems? Well, search, in my mind, is also a very important data structure, in this case, inverted indices. A very important data structure to solve at scale recommender systems as well. So what, posting lists or inverted indices is essentially, saying, here we have some token, or in this case, some words, and I will keep the position and which document in which position these words appear, create an index on that so that when I want to query about a specific word, I can find quickly what documents contain them and where, and then perform advanced and or Boolean operations on them. Typically, the query is in Boolean expression, and you have assignments in the index. That's how typically it works. Now, this work actually that I'm going to talk about here is it's from a paper called Indexing Boolean Expression. It's from the research folks at Yahoo, but basically it's the same use in many places, and this is a public paper, by the way. I mean, published in a very large database, 2009. But the idea here is that you can represent and create a posting list of Boolean expressions, saying, well, turns out that there's an attribute, and the attribute and values, in this case the key attribute 1, and where does it occur? In the expression 1 and the expression 2. Similarly, a assignment of A equals 1 and B equals 2 will have to return back, which Boolean expressions actually match the assignment, right? So let's get a little bit more into how the algorithm works, and this is quite interesting. So basically, you have what's called a K-inverted index construction, where you have initially you have a set of expressions, right? And the idea is to create a posting list. And the posting list is a little bit different than the traditional inverted indexes for search. They're actually saying, well, wait a minute, I want to know the cardinality of the expression, and I want to group them by cardinality. So you see there 0, 1, and 2. So 0 means essentially, in this case, down there, there's a not. So when it's a negative or not in, then it would be considered 0. But then you have all the other ones that are more positive, basically the positive or inclusion expressions are the ones that drive the K. So you have the ones 0, 1, and 2. And then you have a statement saying, okay, what is the expression, in this case, state of California, and I'll talk about the numbers right away, but the state of California assignment or the key attribute value pair actually occurs in the expression number 6, and the operator is, in this case, non-inclusion or not in. Similarly, you see that there's, in the case of age 3, again, it occurs in 1, 2, and 3. And that there is, the operators are inclusion or in. Interestingly, and here's where I'm going to go and talk about relevance ranking, you have weights. Now these weights, we'll talk about how to compute them, but basically there's ways to basically say, wait a minute, the value of someone matching or some assignment matching a particular Boolean expression is different depending on which attribute was matched. So it could be that for a particular case, matching female was more important. Let's say the ad was some kind of female, or related purse or something that had to do with that women like. Then definitely that weight of that attribute is going to be higher. There's also cases where we're stating that there's an upper bound, and you can read the paper. I have references to the paper to compute efficiently as the skipping of some of these evaluation when you are dealing with DNF and CNF forms, basically disjunction, normal form, and conjunction normal forms. But the idea is you have a search algorithm based on this posting list, and by search algorithm and a way to evaluate the posting list given an assignment that essentially produces relevance ranking for you. Now, the score actually can be computed in this following way, and this is again an example. So we say it's and it really brings the same idea as you have with information retrieval or regular search. You have two kinds of weights. One weight is that you can associate with the assignment values. So you could say, I have an assignment, age 1, state of New York, gender, female. But I know more information about the user. I want to compute weights, and by the way, these weights could be, and I will explain, could be computed on the fly based on models. To basically, or neural networks is one of the examples where people are computing these weights on the fly based on evaluation, saying, based on what I know about the user, what I know about the information, the model that I built online, I'm going to interject weights there, and the weights are 1, 2, and 3. I'm just giving an example there. There's also weights that are built based on how much the attribute itself is important when you evaluate the constraint, or in this case, the Boolean expression. Those weights are in the left-hand side, right? So we said, New York, which is, posting list 1, because it appears in the ID 1. New York, something from New York actually has more relevance than something is perhaps from, I don't want to say California, so let's say North Carolina. I hope I don't offend anyone here. But essentially, you have a way to say, if, in this particular expression, there's a pre-computed, weight in the index, which is equivalent to TF-IDF kind of weights in inverted indexes for search. And you have a way to compute weights for the query. And using those weights, you can compute the relevance ranking for a given assignment for each one of the Boolean expressions that matches. In this case, it's a simple multiplication of the weights, and sum of those, basically the sum of the multiplication. In one case, with the Boolean expression 1 for this assignment is 8.1. The Boolean expression number 2 for this assignment, the same assignment, is 1.4. why is this important? Okay, remember that I mentioned that the problem of advertising is finding a match. Well, actually, there's two kinds of matches going on, or two-way matching going on. One is, I have a query, so I know that I want to prevent flash ads from coming back. So I can say, not flash, right, as part of the query, which would go against the attributes of the ads themselves. That's simple because that's traditionally how inverted indexes work for regular documents. Then the other kind of index is, okay, I have document assignments, which in this case, the information about the user. I know that this user is coming from California and female, and I want to obtain the queries, in which case the actual constraints that were defined by advertisers or by the exchange that matches them. And I want to do that in such a way that I have a two-way match to produce a list of top K results. So this is the first part. When I said eligibility, it's actually eligibility with a twist. It's eligibility with some ranking. It's not the final phase. It's the phase where I'm saying I'm going from 1 million items to 100. So it's kind of, that's the phase where I'm coming from. And it doesn't need to be, by the way, you don't have to have all the constraints. It's not about having too many constraints, because it turns out that the ranking is also effective when you're looking at top K analysis for just assignments themselves. So what is an example? So the assignment can be, age 20, country, France, gender female on one side. That's the assignment. The Boolean expression we're trying to match is, age from this age range, and country belongs to or not belongs to U.S. So given an assignment, in this case the supply attributes, sometimes that's how the way they call it, they match the Boolean expression. On the other side, the query doesn't stop there, because the query is also composed from Boolean expressions that are saying, wait a minute, I want ad sizes of this kind, or I want ads that are not flash. So, or I want, certain types of ads that are that have a tag, let's say sports ads. So when those queries come in, then the assignment, in other words, the attributes of the ads are the ones that we're searching, and given a Boolean expression, then looking at the attributes is, and that can be done with any search engine today. When you combine the two, both of them relate to ads. So you basically, what you achieve is a set of ads that match. And the beauty of this is that basically you're done with eligibility, and you have top K ranking of ads that match. Now, once those rankings are achieved, then you have a much more manageable problem. Because after ranking happens, and believe me, it does, people think that recommendations, again, they don't happen in a vacuum. When you're getting recommendations, there's a certain page and placement where you're going to put the recommendations. When you're talking about recommendations, it's not true that it's for anyone. You're putting constraints about who should see this movie or who should see this book. You're putting information about, and I haven't talked about this, these books that I have in my shelf, in this case, the catalog, some of them are going to expire. I have some constraints there regarding budget that I have to use when I select these recommendations. So one important phase is, once you're done with the constraints, how can I optimize for matching or selecting or bidding, creating the bid that will actually help me achieve the best results? Well, the way this is typically done is that there is a value for an action. So in this case, the action could be a click-through. It could be a conversion. It could be that the person actually signed up for the book, author coming from and having a talk on the book. So typically these actions actually don't happen just once. They're chained. So it could be that a person viewed an ad, and then they signed up for an email, or they view it, they clicked on it, and they then convert it. So the idea here is that the bid, and this is a simplistic model. There's much more complicated models for computing bids. But the simplistic way of seeing this is that if you have an action rate, or a probability of that action occurring, which you compute with your offline models, and you have the intrinsic goal value that the advertiser, in this case, the cost of the book, or the cost of the movie, has, or the, how much I value that someone clicked on something. Then you can sum up the multiplication of the action rate times the goal value to compute a bid. And that bid is what's going to compete with all of the other bids for the different items. Now guess what? If someone puts out there a book that is that's $100 book, that's pretty expensive. So you may say, well, the $100 book actually is going to always win, right? It's the bid is highest. No, it turns out it depends on the action rate. It could be a $100 book that no one buys. So these are the things, and by the way, this also has to do with the way people or the system does explore, exploit. Initially, you don't know anything about the book, so maybe it's kind of, okay, let's recommend it to try it out, to explore about it. But it turns out that immediately you get some feedback, especially if there's a long number of users, and you can compute offline, of course, the models for the actions rates, and incorporate that so that dynamically the bids change according to the feedback that they're getting from the users. And this is where the event and the machine learning part takes place. But again, you're only doing this with the top K. Because if you were to do this with all the items you had, it would be quite hard to compute, even real time. Now remember, we have constraints on the memory so that we can include these models inside each node. And they have to be computed, and the bid has to be completed in milliseconds. Talking of which, collaborative filtering machine. By the way, collaborative filtering is great. No one is saying collaborative filtering is not the way to go. I'm just saying you can apply it. You can apply machine learning to compute the models for multiple of these problems, right, offline. But don't try to solve everything with that hammer, because when you come down to doing a scalable system, it's not going to work. So in this case, what are the things that machine learning and collaborative filtering can help us with? First of all, how much weight, what are these weights, right, for relevance ranking? I can have a neural network computing how much weight should I ascertain to the query, the assignments, so that next time when the user feedback comes in, immediately change those weights to be able to basically produce different results. I can have the click-through model, right, the CTR action rate, computed based on all the signals that I have, the time of the day, the website, the kind of campaign that was being run, all these information, get the signals that I get from the live system, process them, build a regression model, a complicated Bayesian network or algorithm, and compute the models to establish or compute the probability of that click-through to happen based on past models and a window of time. And again, attribution comes here, because in order to ascertain that an action has completed, I need to know when that action actually is attributed, or who is it attributed to, because and it's not only the advertisers, the actual ad, which one of the ads were really relevant and made a difference, right? So the other thing is not only action rates, but there's a further problem, optimization. And these optimizations are specifically to delivery and availability. So when you think about recommending movies, turns out that movie catalogs are not something that is static. Another problem with old school recommender systems. They say, oh, here's the movies that you have, and here's the users, and here's the matrix. Go ahead and compute. Turns out that movies have a window in time in which, by contract, they can be sold or even appear. The first, it's a first release. You can only have this movie for 2 weeks. It's going to be in your catalog, great, but you have the rights to show it, for a period of time. So the closer you are to the finalization of that period, you have to take that into account whether you want to do optimization on budgets. So think about budgets. If you have budgets, you're basically assigning budgets to these items in order to do optimization. And obviously then the other one is return on investment for the advertisers and optimization of revenue. Yes, if I have the chance of recommending 4 items, more or less they're relevant. Which one should I choose? Probably it's the most expensive item, right? Because in that way I produce more revenue for as a cross-sale or an upsell of a product. So these things, there has been research that people are doing a lot of work on machine learning, collaborative filtering to compute this. All I'm saying is that it could be tied, and the way to tie it is inserting and computing the weights for the inverted index model to compute the top K, and then also use more predictive analytics or predictive algorithms to work on those top Ks to deliver back the best bid in a way that, similar to what I said in terms of the value assertion. Finally, there's explore exploit. So I mentioned, which actually is interesting because when you have certain signals, you also know which signals have not been utilized more. So you kind of have, there's various techniques, but kind of try to reduce basically the variance and in your data, right? So to reduce variance, you try to get more data points of a certain type. So in order to explore, instead of just exploring randomly, you could explore looking at the variance that you have on the data for certain attributes, and then explore that way, and then get back the information. Again, this is part of the learning or the predictive analytics part used after you, or during the decisioning. And again, the final result is the index and the model are put together and loaded on these distributed nodes to be able to scale and run advertising and recommender system in a way that they're relevant to the user. So what is my recommendation to people that are doing recommender systems? Don't think about this as just a, a academic exercise. Think about this as a business. Recommender system is as important, if not more, I mean, to some extent, it's kind of the same line as regular advertising. Because you have this notion, and by the way, a lot of the times, and I know this because I've seen recommender systems that have been built, they're like overrides by some content folks that think that these are the best things to put out there. So in terms of recommender systems, there's constraints. Guess what? Those overrides are constraints. They're saying, I want to give priority to this set of items. So you need to be able to think about recommender systems in a way that is different than just a matrix of rankings. The other thing is that you're going to apply these constraints, whether it's geolocation, time of the day, in a way that they have to scale. And the way to do this is, well, thinking that all items are not created equal. So when you talk about items in the recommender systems, we talk about ratings, but we don't talk about the value of the item. So when we're talking about advertising, we're talking about a value that's computed and expressed through a bid. So here's where bidding, or the economics and the design of mechanism design and these theories come into place. What kind of mechanism designs will be used for recommender system? Interesting research topic. So because now you can translate a ranking and view it as a bid that is satisfying the constraints that are being defined and achieving an optimization towards a goal. And finally, some of these things like budget have a direct translation in recommender systems. A lifespan of the ability of the life shell of it. So I put up a little summary. Sorry, I misspelled that. So basically, you have like targeting translated into recommender systems constraints. Budget, for example, availability. You have a bid in terms of a ranking or a score, relevance in recommender systems. You have an action, what did the user do, a selection. But now we're talking about multiple actions in advertising, right? We're not only talking about, a ranking or a rating that the user gave. Although in recommender systems, to be fair, there's this explicit ranking that is achieved by looking at different events. So it's kind of similar. And then finally, the models, instead of being a models that you try to just do one model and that's it, here is actually models and indexes. I didn't include that, but in advertising, you use the index, and in recommender systems, you can use an index to shrink the space that you're searching and come back with relevant recommendations. So the idea, the final kind of message is that if you build this, then guess what? You're building an advertising system, a recommender system. You have search because you kind of had to index your metadata anyways. And because you're gathering information about what the user did, you've solved your business intelligence problem. Finally, let's talk briefly about evaluation. because recommender system has this problem that you have to have a set of ratings to make sure you kind of understand how your algorithms did. So kind of a golden set, right? So they have movie lens. And they said, here were the rates that you had. And you kind of separated in training and test set and do the machine learning and then go against the set to see how you did, right, in terms of the test set. What happens in real life is there is no golden set, that you kind of have to have a way to measure and do bucket testing or A/B testing of your models. Sometimes you can actually do this offline. So here's an example. So I have, ad server, which has a bucket of users that it's evaluating a new algorithm, right? So we have this, information that we can replay, say recommendations that happened, and we know what happened. So we can create traces of those things and replay them later to evaluate new algorithms. This is offline. But in the same way, online, you kind of have to have buckets where you're applying different algorithms and seeing how one does better than the other. So from that perspective, offline evaluation is not a golden set per se, but the golden set actually is created from the system itself. In other words, you kind of record what was that the user did and evaluate constantly your algorithms, basically joining the events data with the responses that the user did to produce an offline evaluation. If the model is good offline, then you can promote it to online evaluation. So that's how advertising actually works. And if you do this for recommender systems, you have a way to actually build systems that have evaluation of how they're doing without having to artificially create or get ratings from a data set perspective. That's about it. What's the big fish? Well, doing all this for online TV. That's kind of the way I see it. It's really interesting, actually, problem. For over-the-top internet TV, you have constraints that are what are the programs, what are the promos that you can insert, what kind of movies, and and what do you want to cross-sell, upsell, what are the ads you want to construct and put into all these systems. Thank you. Yes, go ahead. So let me try to understand let me try to rephrase the question. So you're saying when you have different, let's say, players or different actors, the advertiser, the publisher, the exchange, the question is, are all the models the same?
Yeah, or whether when they have partial information, what's your recommendation?
Yeah. So it's an interesting problem. So from an exchange perspective, which tends to be neutral, not really, but basically when you have an exchange which sits in the middle, you have the publisher trying to gain as much revenue as possible. You have the advertiser trying to make sure that the advertisement, the money they're paying for their advertising is well spent. So each one of them have actually partial information because the publisher doesn't know everything about the ad, and the ads, the advertisers doesn't know all the stuff that the publisher knows about their users. So that's where an ad server or an exchange comes into play, and they know about all that to construct the model. So then there's multiple pieces that construct the bidding. I didn't explain all the part on the bidding side, but you have things like reserve price from the publisher side. So how do you compute the minimum price that publisher is willing to give this opportunity for? And you have things like dynamic prices that depends on the budget, which is more on the advertiser side. So yes, each individual systems know little. Sometimes they go through third party. So the advertisers may not know much from what the publisher knows, but if they go through BlueKai, remember I said about the data provider, they can know enough to kind of come up with a bid that makes sense. And then the auction takes care of resolving what the final is. The problem is then, is the bid correct? The bid will autocorrect itself based on the feedback that is given by the user. So yes, the different models depends on who are the players.